2. Refraction of waves. Refraction of waves is due to change in speed, which is usually due to change in nature of the medium, such as change in depth of water for water waves. If the wave hits the interface at an angle, the change in speed will then result in change in direction of propagation. Let's take a look at the following video. Experiment 5C. Refraction of water waves.
We will see how water waves are refracted in different situations by using a ripple tank. Put a perspex plate in the ripple tank and pour water into the tank so that the water is shallower over the plate than elsewhere. Send straight waves to hit the straight edge of the plate head-on. What happens to the waves in the shallow region? Send straight waves to hit the edge of the plate at an angle. Observe how the direction of travel of waves is changed when water waves pass from deep region to shallow region. Straight waves are sent to hit the edge of a lens-shaped perspex plate. What happens to the wave after passing through the lens?
From the video, we can see when the depth of water changes, the speed of water wave will change. Then a change in direction of propagation may be resulted. A. Change in wavelength and wave speed. From the experiment, we can see that the wavelength decreases when the water depth decreases. As the frequency of wave cannot change, there must be a decrease of wave speed, as according to the equation V equals F lambda. In other words, as the speed and wavelength are directly proportional, when frequency remains unchanged, the ratio of speeds equals the ratio of wavelengths. And therefore, we have the following relationship, that V1 over V2 equals lambda 1 over lambda 2 as frequency remains unchanged. For refraction of light, we call the ratio V1 over V2 refractive index, in which V1 is the speed of light in vacuum or air, in which light travels from vacuum to another medium such as glass. Example 2. Water waves crossing a boundary. For part A, the block is a transparent block, which results in a shallower region, in which wave travels slower and so the wavelength is shorter. For part B1, frequency does not change in refraction. For part B2, which is the most difficult part, you have to find the refractive index from the left to the right, which means the ratio V left to V right, or lambda left to lambda right. As lambda and speed V are directly proportional as mentioned above. B. Change in wave direction. Change in direction will be resulted when wave travels across an interface at an angle. On the other hand, When wave hits a interface perpendicularly, it does not change in direction. In other words, refraction does not always result in change in direction. But how change in direction is resulted? Let's refer to page 51 again. The water wave hits the interface or boundary at an angle. When the wave enters the shallower region, it travels slower than the part still in the deeper region, which then results in new wavefront direction. Eventually, a wave bends towards normal when it travels from a faster to a slower region. Similarly, we may also explain why a wave bends away from normal when it travels from a slower to a faster region. While it sounds straightforward, you have to learn the skill to draw the wavefronts in these situations. To start with, you have to identify the fast and slow regions. In this case, the wave travels from slow to fast regions, so it should bend away from normal. So you must draw the incident ray, and then the reflected ray. Lastly, complete your diagram by drawing the incident wavefronts, and then the reflected wavefronts, in this way. Do checkpoint 3 below.